Hello, this is Ms. DB. Today we're going to talk about Chapter 11, Section 6, which is on segment relationships in circles. The last couple sections we looked at angle relationships and how the angles are related to their intercepted chords. Today we're going to look at segment and the lengths of the segments and use those to find problems. To solve problems. I think I said find problems. So our vocabulary today is secant segment, external secant segment, and tangent segment. In 1901, divers near the Greek island of, I should have practiced this word, Antikythera, discovered several fragments of ancient items. So just pieces of things that used to be whole. And they were able to use the math that we're going to go over today to be able to figure out the diameters of the complete disk and to really find out what is the size of the actual object if they only had a piece of it. So here's a theorem that has to do with the four segments that describe the relationship among the four segments that are formed when two chords intersect in the interior of a circle. All right, so here's an example. We have chord CD and chord AB intersecting at point E. There's a relationship with the pieces. There's four different pieces shown by green, blue, red, and purple. And the relationship is if you take the red segment from A to E times the blue segment from E to B. So these are pieces of the same segment. If you take those pieces and multiply them together, it will be the same as CE times ED. So piece times piece equals piece times piece. All right, let's see this in action. We want to find the value of x. X is from J to H, and the 14 is from J to G. Sometimes it's a little tricky to know what the numbers are labeling. 7 is J to F, and 10 is J to E. So all we have to do is multiply piece times piece equals piece times piece, making sure that when we multiply the two pieces, they're of the same segment. So 10 times 7 equals 14 times x, and then we just divide by 14 to get that x is 5. They also want us then to find the length of each chord. So from J to H is 5. So the chord, remember chord goes from one point on the circle to another point on the circle. So chord GH is going to be, 19, sorry. You have to add the two together. And then chord FE would be 17. So don't forget to do that last step of finding the lengths of the chords if you are asked to. All right, in this question, same thing, find the value of x and then find the length of each chord. So to find x, we remember that piece times piece equals piece times piece. So 6 times 5 equals 8 times x. So 30 equals 8x. Divide by 8. We'll get a decimal, but that's fine. You'll often get decimals for these. And then to find the lengths of the chords, we already could find AB is 11. And then we take 8 plus 3.75 to get 11.75 for the length of chord CD. All right, here's an application problem that is in your textbook, and this is what we were talking about that fragment of an ancient disk. So let's see how they were able to find the diameter of this disk, even though all they had was this little piece. They were able to find that from here to here was 5, and that this was 3. Now we learned a theorem that the perpendicular bisector, they measured this and it was 90 degrees. So then they know that this side over here is 5 as well. This was in an earlier section in this chapter. This chord was bisected since it's perpendicular here. So we have 5 and 5, so this chord is 10. But remember that the theorem is that piece times piece, let's call this x, is equal to piece times piece. So 25 is equal to 3x, or as they wrote QR, divide by 3, and you get 8 1/3, or 8.33333. So then we can find the length all the way from P to R by taking 3 plus 8 1/3 and get 11 1/3. And that is the diameter because we found that this was perpendicular here, which means then it's the diameter. All right, this is just another problem, but let's say we have a different measurements. So now we have 6 and 6, or 12 from here to here, and this is still 3. So how would that change the size of the disk? Will it be bigger? Will it be smaller? What do you think? So we again use the theorem that says that the piece times piece equals piece times piece. So 6 times 6 equals 3 times the missing part, or 36 equals 3x, divide by 3, and you get 12 for this. And then to find the diameter, that was 15. Well, the other diameter, the one we just looked at, was 11 1/3. So the difference, how much longer is the disk diameter, is 3 2/3 inches. This one is 3 2/3 inches bigger than the other disk. Little bit of vocabulary here. A secant segment is a segment of a secant with at least one endpoint on the circle. An external secant segment is a secant segment that lies in the exterior of the circle with one endpoint on the circle. So let's look at this. We have two secant segments here. We have PN and we have NM. They're both secant segments. This one is the external. The whole segment, the whole secant segment goes from here to here. I'll call that the whole. We also have K, I'm going to use a different color here. We also know that KJ is a secant segment and JM is also a secant segment. This part is external, and I'm going to call M to K, that's our whole secant together. So the theorem is this. If you have two secants intersecting in the exterior, outside the circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. Okay, so whole external, or they're calling it outside, equals whole outside. Let's look at this. I'm going to do red for the top one, the ABE one. All right, so we have, here's our external part, BE. That's our, I'll call it outside like they did. Times the whole is both of those parts together. If you multiply the whole times the outside, that will equal the whole of the other secant segment. See that whole thing? Times the outside part of it, the external segment. So let's see how this is going to work. I can't erase this? That's weird. No eraser allowed. Maybe I can erase it. Oh well. Okay, so ignore those lines. They're stuck there now because I accidentally hit. Oh, they went away. Great. All right, so we are going to take the whole times the external, which is 8, will be equal to the whole times the external part. The whole in GE is x plus 8, not x times 8, x plus 8, and we have to multiply that by the external part, which is 8. That will be equal to the whole of DE, which that one we can add together, 9 plus 7. But I'll write it for now. 9 plus 7 is 16 times the external part. So we have 8 times x plus 8 will be equal to 16 times 7. You can then distribute through 8x plus 64 equals whatever. Or you could divide this both sides by 8 right now and make it an easier problem. X plus 8 would be equal to 14, so x is equal to 6. They ask us to find the value of x and the length of each secant segment. So this GE would be 14, and DE we could have already found was 16. That one you can find even before you find x. All right, let's look at how they did it. See if they did a shortcut or nope, they multiplied through. But that's okay. If you multiplied through, then you have a two-step equation. You would subtract 64 from both sides and get 48 equals 8x, and then divide by 8 to get 6 equals x, just like we got. And then you find the length of each segment, secant segment. Find the value of z and the length of each secant segment. Same thing. You have to take the whole times the external part is equal to the whole times the external part. So we're going to have z plus 13 is equal to, or z plus 13 times 13 is equal to 30 times 9. 39 times 9. I forgot to add these two together. 39 times 9. And then you can see this would be so much easier if you divided both sides by 13 right now. If you divide both sides by 13, and I don't know if this will always work, but we would get 3 here, and then we would have 27 equals 13 plus z. Might as well make it easier if we can, and we get 14 equals z, which is the same thing they got. And then we have to find the length of JG, which is 27, and LG is 39. So here's a tangent segment. It's just a segment of a tangent with one endpoint on the circle. So here's where it intersects the circle. And there, of course, the angle formed would be outside. And you might expect that this is going to be a pretty similar theorem as the other one. However, it's all external. There's no, in the secant ones, there was part of the segment was inside the circle, and we had to take the whole thing times the external, the whole thing times the external. Well, it turns out with tangent, we do the same thing. We take the whole times the external, but the whole and the external are the same thing because it's all outside the circle. So you take the whole times the circle times the whole times the circle. The whole times the external equals the whole times the external. If one of them is a secant and one of them is a tangent, when you do the outer times the whole thing, it's the same thing, so you can write dc squared. So here we have a secant and a tangent. We take the whole times the external equals the whole times the external. Well, the whole and the external are the same thing, so you can write x squared. So that would be 20 times 5 equals x squared. Now, sometimes, since we have an x squared, we will have to take the square root of both sides. And in this case, we would get 10 or minus 10, but negative 10 doesn't work in this case. Sometimes you might have to simplify your roots here or do a little bit more algebra in order to find what x is. So in this one, we would just get 10. Now, in this one, they didn't ask us to find the length of each segment, but it wouldn't be hard to do. This time, the variable is part of the secant. So we have the whole times the external equals the whole times the external. It's just that they're the same thing. It's not really a different formula or a different theorem. It's just that the whole and the external are exactly the same amount. So in this one, it doesn't do me any good to divide both sides by 7 because it's not divisible. It doesn't give me anything nice. So I'll write 49 plus 7y equals 100, and then I'll continue to solve. So 7y equals 51, and you're going to get a decimal for an answer, which is just fine. They wrote it as a fraction, but you can write it as a decimal. If you do a decimal, round to two decimal places or to the nearest hundredth. And that's it. They don't get a whole lot harder than this. So you won't have too much trouble with this assignment. I do want to show you one example they didn't show. If you have two external or two tangents, let's say this is x and this is 9. This is going to be kind of funny. You're going to be like, oh yeah, of course. So then you would have the whole times the external, which is x times x is x squared, equals the whole times the external equals 9 squared. So x squared equals 81, so x equals 9, because these are congruent. So there's kind of a shortcut theorem that you've already learned that maybe you remembered. All right, so thanks a lot and have a great day. Please ask if you have any questions on this assignment.